Inverse functions. Not every function has an inverse function. All right, so that's what we want to preface this by. Is not every function has an inverse function. Notice it doesn't say not every function has an inverse. You can find an inverse, but that inverse may not be a function. So what we're looking at are inverse functions. So it's a special case scenario with certain functions in which their inverse is also a function. And those types of functions have a name. They're called one-to-one functions. One-to-one functions have inverse functions. One of the tests that you can use for one-to-one functions is, remember when we were testing for functions in 100, we used that vertical line test, and if it crossed it more than once, then it failed. With one-to-one functions, it's going to pass the vertical line test, but it's also going to pass a horizontal line test that follows the same rules. Horizontal line test and vertical line test, they follow the same rules in the fact that you've got to, you can only touch in one spot vertically, and then when you do the horizontal lines, you can only touch in one spot horizontally. Horizontal line test. So here's an example of a function that might fail the one-to-one test. Okay, so let's take simple parabola. That definitely, we know that's a function. It would pass the vertical line test. If we drop vertical lines, no matter where we put it, it only touches in one spot. But if we checked it with the horizontal line test to see if its inverse was going to be a function, we can find several places that it's going to hit twice and it fails. So this would be a not one-to-one. Doesn't mean it doesn't have an inverse. Just means that the inverse is not a function out of that. So we're relying on the fact that the one-to-ones have inverse functions. And then here's an example of an easy one that does pass. And that would just be a nice, simple, linear graph. That passes the vertical line test, and it passes the horizontal line test easily out of that. So this is a one-to-one function, which means the inverse of that, whatever that equation is, we could find the inverse of it, and it would be a function as well. That's what we're finding there, okay? And when things have an inverse function, it makes the world spin on its axis at the right speed and all that stuff. All the things line up mathematically that happens there. And it's just a special case type scenario out of that. So we're going to be checking some functions to whether or not they're one-to-one. And then we're also going to find the inverse function that goes with those things today in this section. So let's just start with the easy idea of testing one-to-oneness with, and we're going to utilize the graphing calculator to help us do that graph, because that horizontal line test is super easy to check. So I think it's the easiest thing to do is graph the thing and see if it passes it. If it doesn't, hey, it's not one-to-one. We don't have to find the inverse function. We can work with that. So let's look at doing that with our graphing calculator. So test a function to determine if it is 1 to 1. All right. So example A, let's just start with this function. F of x is equal to negative 4x plus 12. Real simple equation. It's linear. We know that just because of the form that it's in. But even if we don't know that, we've got this graphing calculator tool that helps us. remember that f of x, that's the same thing as y. So I'm just going to take this thing and I'm going to go to my y equals menu on my calculator. We'll clear out all this other junk that I was doing before. And I'm just going to graph that simple equation, negative 4x plus 12. Hit graph. And then I'm going to check it with my horizontal line test. They have already written it in function notation with the f of x there, so we know it's a function, so we don't have to test the vertical line test. Does this pass the horizontal line test? That no matter where I lay a horizontal pencil on there, it only touches in one spot. It's not going to hit it twice. So this passes the horizontal line test and is 1-to-1. So it's yes, it is 1-to-1. Determine if it's 1-to-1. Yeah, that one is. Okay. Example B. Say we had the square root of 25 minus x squared. Square root of 25 minus x squared. All right. Graph that. I'm just going to clear out this other one. We get a square root symbol. So second x squared button. 25 minus x squared. Hit graph. Does that pass the horizontal line test? No, definitely not. I could draw a line right there and hit it twice. So that definitely fails the horizontal line test. So this is a no, not 1-to-1. Or I just write that not 1-to-1. Let's look at something that might be kind of weird looking, but it's part of the game. So let's say we had maybe parentheses x minus 2 squared plus 5. And then they say if x is greater than or equal to 2. Maybe that's what they've given. So it's almost like a piecewise defined function, but it's only got one piece. So it's similar to the piecewise defined function in that it gives us a restriction on the domain of this, but it's only got one piece. So when I go to graph this to test it, I've got to take into account this inequality that's out here. Okay, so I only need the x's that are greater than or equal to 2. So when I go to graph that, I've got to be able to do that. So I'm going to have to take parentheses and then double parentheses there and then it's x minus 2 squared plus 5. So remember what that is. X minus 2, close the parentheses, squared, and then is it minus 5 or plus 5? Plus 5. Plus 5. Close the parentheses, divided by, and then I'm going to put that inequality that x has got to be greater than or equal to 2. 4, 2, and hit graph. And notice it looks like I'm getting half of a parabola there. Does that pass the horizontal line test? Yeah, it does. Okay. If I did not have that restriction with that inequality, if I took that off of there and I didn't type that in, so this one is yes on that, so yes. But as kind of an extra side example, if I did not have this inequality stuff out here, if I deleted that, and just graphed that original, that whole equation, does that pass the horizontal line test? Definitely not. So anytime they put that after that, that's going to be an important thing. So you've got to pay close attention to that and account for it when you're doing that. So be careful of those things when they put an inequality out there. Sometimes they'll put if when they write it. Sometimes they may just put like a semicolon and then put the inequality after it just to save ink when they write those problems there. So either way just means, hey, take this into account, that inequality there, because it means something to this. All right. So just determining if something is 1-to-1, just simply look at the graph and try that horizontal line test. That's the best way to determine if a function is one-to-one. A single function is one-to-one. All right. All right. Next thing we want to talk about are finding inverse functions. So finding the inverse function. So that's kind of the heading here. One thing that we have to know about inverses swap the domain and range. Domain being X, range being Y, right? We know those go together. Domains are X's, ranges are Y. So inverses in general will swap the X and the Y's, or the domain and the range. All right. So if we're going to find the inverse function, that's the first thing that we need to do. We need to swap X and Y values. All right. And now when we've got an equation, that doesn't necessarily look easy to do. We're gonna look at that and determine what we can do with that. But that's the key thing to remember is inverses swap X and Y. So anytime you got to find an inverse, swap X and Y and work from there. Okay, so that's the first thing that you want to do there. Inverse functions, that's another thing that we're going to build through here. Inverse functions compose, so this is where the composition relates, compose to give X in either direction if F composed with G of X equals X and G composed with F of X equals X. Then F of X and G of X are inverses of one another. All right, so let's take these ideas and start putting it to some functions and see what's going on. All right, first thing we're going to do, we're going to decide, are these two functions inverses of one another? So are these inverse functions? Okay, and the way we're going to test it is using that composition idea. All right, so let's start with this one. F of X is equal to 1/8 X minus 5/8, and then G of X is equal to 8X plus 5. All right, so if we're going to verify that these are inverses of one another or that they're not, we don't know that for sure. So we're going to do that composition. We're going to do F composed with G of X. We're going to do that work. And then we're going to do G composed with F of X. Do that work. Now, what's going to happen, if one of these fails, then the other one will automatically fail too. Okay? So if when we do this first one, it doesn't turn out to be just plain X, then we don't have to do the other one. Okay? So only time we need to do both of them to verify and actually prove that they're inverses of one another. That's part of the game there is proof. And you have to show both directions for proof. Just to answer whether they're inverses or not, I'm good with you doing one direction, but proof is that you got to do both directions. Okay, so let's do the F composed with G direction here. So that means we're taking g of x and putting it into f of x. So 1 over 8, and then we're putting 8x plus 5 in for x, and then minus 5/8. So the fractions in there can make it ugly, but it actually works out really nice here, because when I distribute the 1/8, 1/8 times 8x, well, that'd be 8 over 8x, which is just x. 1/8 times 5 over 1 would be 5 over 8. So 5 over 8 plus there. And then we've got the minus 5 over 8, which what happens to both of those? They cancel one another out. And there's plain old x. Check on that direction. Let's go the other direction and do g composed with f. So that means we're taking f and put it in the place of x in g. So 8 parentheses 1/8 x minus 5/8, and then plus 5. So we're distributing an 8 to both pieces there. So that'd be 8 over 8x, which is x. That'd be minus 5 and then plus 5, and those cancel each other out, and there's x. This verifies in both directions. So that means that f of x and g of x are inverses. So that's verifying that two functions are inverses of one another. They're not going to note them as inverses, like f and f inverse. They're going to say, here's f of x, here's g of x. Are they inverses of one another? If you get anything other than plain x, then it's not. If you get a negative x, they're not. If you get x plus 1, they're not. Anything else other than plain x, they're not inverses of one another. Okay. Let's take little tougher one here. F of x is x cubed minus 1, and g of x is the cubed root of x plus 1. So cubed root, maybe not as familiar with it. It's just like a square root, except for we're looking for cubes. 27, the cube root of 27 is 3, that sort of thing. All right, so let's take f composed with g, and let's go that direction first. So that takes g of x and puts it into this. So the cube root of x plus 1, and we're cubing that. So when I cube a cubed root, it's just like squaring a square root. They go away. They cancel each other out. So this cancels the root and leaves me x plus 1 and then a minus 1. Hey, the ones cancel each other. That's x. Check in that direction. Proof is to check it in the other direction. So I'm taking f and going into g. So that's going to be the cubed root of x cubed minus 1 plus 1 underneath the cube root here. So like terms on the inside there, the cube root of x, the ones and ones cancel out. So the cube root of x cubed, just like the square root of x squared is x, so is that. So it verifies in both directions. So f and g of x are inverses. Say we had f of x is equal to 5x minus 2, and then g of x is equal to 1/2 x minus 5 over 2. Those look similar to the other problem we did, like there might be inverses of one another, but there's no way to tell unless you actually do the composition, or that's the algebraic way to do it. It's our f composed with g of x. Let's do that direction first. So we're taking the 1/2 x and the 5 over 2 minus 5 over 2 and put it into the place of x here. So 1/2 x minus 5 over 2, and minus 2. When I work that out, I get 5 over 2x minus 25 over 2 minus 2. It's easy to see that even before I finish simplifying that I'm not going to get plain x, right? Negative 25 over 2 minus 2, that's definitely, 5 over 2x is definitely not going to go away either. So that'd be, that's 4 over 2. Be negative 29 over 2. Not x. That's what we're seeing here. So that tells me right there, I don't have to do the other direction. These are not inverses. Not inverses because the composition doesn't give me plain x. So not a hard test. Get you a little bit more practice with that composition. So, one of the tougher things from the previous section. But they're not going to be too crazy with how hard the problems are with this part. We're verifying inverses out of that. All right. Now, let's actually take a function that we know is one-to-one and do the algebra that it takes to find its inverse. So we're going to take a function and build the inverse from that if it's one-to-one. Okay, so find the inverse function if the function is 1, 2, 1. Okay, so the first thing that you're going to check there is the function one-to-one. Okay, so before we start, we need to check that. So f of x is equal to 3x minus 7. So I'm going to check that for one-to-one test. The way I check that is I graph it. So y equals 3x minus 7. And check the horizontal line test on that. And it passes. So this is a one-to-one function. So I can proceed with finding the inverse. So inverses swap what? Domain and range, right? So they swap x and y. So when you're going to find the inverse on your own, you're going to swap x and y as the first step. Is I'm going to put an x over here and the y where the x was. Because that's what an inverse does, is it swaps x and y. The next thing that I need to do is solve for y again. So I'm going to take this blue equation. I'm going to get y by itself. If I can get y by itself, I'll have the inverse function. That's what I'm looking for. Okay. So the first step is move stuff that doesn't have a y. So I'm going to move the 7 by addition. So x plus 7 is equal to 3y. And then to get rid of the 3, I'm going to divide everybody by 3. And there's y by itself. I got 1/3 x plus 7 over 3, because that's a 1 in front of the x there. So I'd rather write it 1/3 x instead of x over 3. Now I want to rewrite this with function notation. So the way you write that, once you've gotten y by itself again, you want to rewrite it with function notation. And the way you write that is f and then like a little -1 exponent. And the way that reads is f inverse of x, because our original function was f. So the f inverse of x would be 1/3 x plus 7 over 3. And that we have found the inverse of that function. Because it was one-to-one, we could find an inverse function. All right. Now, another one. G of x. X squared plus 2. X squared plus 2. I want to verify again that it's one-to-one before I start anything. Because they wanted me to find an inverse function. Is that a one-to-one? No, it fails that horizontal line test a lot. So this is not a one-to-one function. Doesn't mean it doesn't have an inverse, but it means the inverse is not a function for this problem. So, and by the directions that you're going to see, you're not going to have to find that inverse on this problem. We only want to find the inverses of one-to-one functions so that we can find inverse functions, not just inverses. And inverses that are not functions can sometimes cause issues. Okay, so that one not one-to-one, so we don't have to find the inverse function. Can't find the inverse function because it doesn't exist. Let's look at this one. H of x equals x minus 3 to the third power. So this one's going to take us a little deeper into some algebra here and see if we can't work that out. All right, so let's graph that, see what's going on with it. Clear parentheses x minus 3 raised to the third power. So pretty simple equation looks like. And it looks like it gets kind of flat right here in this little change of direction there. But if you zoom in there at that spot, oops, too far, you'll kind of see that it doesn't get, it's not perfectly flat. The more you zoom in, the more you see that, hey, there is a curve to that. You know, it's still curving there, even though I've zoomed in quite a lot there, that it's curved there, not perfectly flat. So it does pass the horizontal line test for this one. Okay. It's always called a question on that, whether it passes horizontal line. Yeah, it does. You got to zoom in there, and you can see that it doesn't. Most of the ones that you're going to see, if they fail the horizontal line test, it's pretty obvious that they fail it. They're not going to put borderline things there for you to test, because we're really after you practicing finding inverses. So again, we're going to start out with our first step being swap x and y. And this is where, you know, you may not have done this before in a math class, depending on how far you've come, or when you had algebra 2, whether they taught this or not, because this sometimes was taught in algebra 2, is now anyway, but it was an advanced math topic just a few short years ago, actually. So first step would be getting rid of the cubed. So to get rid of a cubed, it's kind of like getting rid of a squared. You take a square root to get rid of squareds. You're going to take a cubed root to get rid of cubes. And the nice thing about the cubed root is that you don't have to deal with the plus and minus like you do with the square root. Remember, we took square roots to solve quadratics. You had to put the plus and minus in front of them. You don't have to do that with cubed roots because they keep the sign of whatever the number is. So the cubed root of x is now equal to y minus 3. And that's pretty easy to get y by itself now, because all you got to do is add 3. And that 3 does not go underneath the cubed root, so it's cubed root of x, and then a plus 3 on the outside is equal to y. And that, rewrite that as, this is h of x, so it's h inverse of x equals the cubed root of x plus 3. We found the inverse function for that one-to-one function that we're dealing with there. Okay. All right. So everybody's favorite. We'll do a couple of these actually. A lot of people think these are the most difficult inverse functions that we deal with here. And I won't disagree that they're difficult, but once you see the idea of it, every one of them works the same way. So it's not as bad as some are. So let's start with this. F of x is equal to 2x plus 3 and x minus 4. And they tell me that x does not equal 4. Why do they tell me that? What part of that equation makes it where they have to say x doesn't equal 4. X minus 4 in the denominator, that bottom part there is the issue, yeah. So they're just telling me, hey, there's a restriction on the domain there. That x can't be 4 because of this stuff that's in the bottom. It doesn't affect how we do this problem. So if I graph this, I'm going to graph parentheses 2x plus 3 divided by parentheses x minus 4. Hit graph. It creates this sort of graph. We're going to talk about this kind of graph later on in the semester, a couple of weeks actually. Oh well, not a couple of weeks. Next week we will talk about this a little bit with that kind of a graph and how that works. But it passes the horizontal line test is what happens here, and this is a one-to-one function. So we can find the inverse of this. So we're going to again take our idea of y and x and swap them, but we're swapping this x over here, and then y goes in both places where there was an x on the right hand side, and that's where this gets confusing for some folks. But if you'll stick with me here, I think I can show you. You know, it's a step-by-step process to get rid of the get y back by itself. All right, so first thing that I would do is I would multiply by whatever's down here. I'm going to multiply both sides by y minus 4. Okay. That'll leave me 2y plus 3. And on the left-hand side, I'm going to go ahead and distribute x to both of those. So that's xy minus 4x. Okay. So multiply by whatever's in the bottom. That's the first step. And then distribute on the left side. Now I need to move things that have y's together and things that don't have y's together. That's my job. I need all the y's on the same side. So things that have y's are this piece right here, the xy, and that 2y. So I'm going to move the 2y by subtraction. So that's going to be xy minus 2y minus 4x equals 3. So I'm just doing one thing at a time. So I'm moving the y stuff to the left. The things that don't have a y at all are going to the right. So I'm going to move this 4x by addition over there. So that's going to give me xy minus 2y is equal to 4x plus 3. So we can see I have everything that has a y's on this side. Things that don't have y's on that side. The next step is to factor a GCF out of the left-hand side. What's the GCF of xy and 2y? What do they both have? They both have a y. So I can factor out a y, and that's going to leave me x minus 2 in there. And now I can get rid of the x minus 2 by doing what operation to leave y where it's at? But think about if I had this problem. How would I get y by itself on this problem over here on the right? Divide by 3 because it's the part that's not y, right? That's exactly right. That's the idea. Is same idea. We're just dividing by something that looks a little weird. These cancel out, and there's y by itself again. So the inverse, f inverse of x, is 4x plus 3, or x minus 2. And what should I tell them that x can't equal? 2, because that's what the bottom part, that's the issue with what I've got left over. Okay. Yeah, that's not easy, but it's the same process every time. I'm going to do another one similar to that. Different letters or different numbers, different pieces. Okay. So let's look at another one like that. What was that? Okay. Let's say we had g of x is equal to let's do x minus 5 over 3x minus 8, and x cannot equal 8 over 3. Not that really doesn't affect this one at all. So again, I'm going to swap x and y. I'll go ahead and tell you this one's 1 to 1. You don't have to go through the step of graphing it. It is 1 to 1. So y minus 5 over 3y minus 8. What's the next thing I do? I've already swapped x and y. So I need to get rid of that fraction stuff, right? So to get rid of fraction stuff, we got to get rid of the bottom. So we're going to multiply by 3y minus 8. So always going to get rid of the denominator. So I multiply both sides by 3y minus 8, like that. Okay? That cancels it out on that side, and I distribute on the left side. So that's 3xy minus 8x equals y minus 5. So I've gotten rid of the fraction looking stuff for a second. Now I need all the y stuff to one side, all the non-y stuff to another side. Okay, so I'm gonna move the y and move the 8x. I'm gonna do it all in one step this time. So moving the y by subtraction cancels it out here. Moving the 8x by addition cancels it out there. So there we got 3xy minus y equals 8x minus 5. Close, very close. What do both of these pieces have in common? Both got y's, right? So that's going to give you 3x and then minus 1, because there's a 1 understood to be in front of that y there, right? 8x minus 5. And then we need to get rid of the stuff that's not y on that side, which is the 3x minus 1. Okay. Divide by 3x minus 1. There's y by itself. 8x minus 5. 3x minus 1. And that tells us, hey, here's the inverse of this problem. G of x, or G inverse of x, is equal to 8x minus 5 over 3x minus 1. X cannot be 1/3, right? Okay. All right. So let's look at one more inverse function, and then I want to show you graphically how you can verify inverses as well. Graphically can sometimes be good, but sometimes it's hard to visualize what's going on there. But I want to show you how you can look at two functions and graphically determine if they're functions or not, or if they're inverses of each other or not. And we're going to use this last example to help us show that. So, example L. Example L. All right, so we got f of x. Let's just make it square root of x plus 5 and x has got to be greater than or equal to -5. That's the only way that that works, domain-wise. So a little easier on the work here. So we're gonna y equals square root of x plus 5, and then swap x and y. How do you get rid of a square root? You square both sides. Okay. So that's gonna give us x squared is equal to y plus 5. And then get y by itself. So subtract 5. X squared minus 5 is equal to y. That's the inverse function. F inverse of x is equal to x squared minus 5. But I've got to have a restriction on the domain here, because I know that x squared minus 5 looks like this normally, right? And that's not a one-to-one function. If the original function is one-to-one, the inverse function has got to be one-to-one too. They're functions, right? So how do I restrict that? Well, I've got to think back at what is the y value in that goes with -5. If I had a -5 in here, because it said x can be anything bigger than -5 or equal to -5. What if it is -5? -5 plus 5 is 0, right? And 0, you can take the square root of 0. It's 0. So this one, x, has got to be greater than or equal to 0 out of that, because it's really the y value from the range that goes with that restriction on the domain. It's the same. They're the flipped of one another. They inverses swap x and y. So that's what's going on there. So that's a little tricky there. Let's look at the graph of this and this on the same coordinate plane with the calculator. So I'm going to graph y equals, I'm going to graph the square root of x plus 5. And then divided by, and then I'm going to put that restriction. X has got to be, second math, greater than or equal to -5. Okay, so I'm going to graph that, and we see that graph. That's what it looks like. Okay. And then on y2, I'm going to graph the inverse function. But I'm going to put that restriction on it as well. X squared minus 5, division symbol, and then I'm going to put x has got to be greater than or equal to 0. X greater than or equal to 0. All right. Now, here's what else I'm going to do. On y3, I'm going to put y equals x. Remember when we do the composition of an inverse and its original function, you get plain x back? That's where that plain x is coming from. When I hit graph here, notice where are they all crossing? Right there on that black line, right? That black line is the reflection line. It's hard to see on the graph like this because the way the calculator orients the graph, it's wider than it is tall. But if I hit zoom 5, it squares it up and makes it perfect. And look how it's a reflection across that line. That inverses reflect across the y equals x line. So there's a graphical way to decide if two equations are inverses. Now, that's handy if they cross real close to the origin there. But when you get one of those rational ones, those ones like what example was it 3 and or example H, or I don't know what letter it was. When you get ones that look like these, like K, those are harder to do because they're so spread out. It's hard to see the reflection out of that. That's why graphically it's not really a great way of doing that. but a lot of times you can check that really, really fast and see if things are inverses of one another. If they cross all like that and there's a reflection across that line, then they're inverses of one another. If there's a little bit off on either side, then they're not. Okay, so that's a handy thing to be able to check there, just for a quick check to decide, oh, do I need to do this composition or not, or is it way off? Because if it's way off, you'll be able to tell. If it's close, you probably want to do the composition with the algebra to verify for sure. All right. So things going on this week. I'm going to put some practice problems here. What you can do out of your textbook on section 2-6, 17 through 41. Odd on all these there. On in section 2-8. I don't want to put page numbers because I think page numbers, but the numbers are different. 1 through 77. And then 4-1, which is the last thing we did. 3 through 87, just some odd ones out of there. And you'll get some practice on that stuff. Canvas quizzes, you got 3 of them that'll are online, and then you got 3 labs that go with this. Straightforward. There's a video already up of those 3 labs, and the document is there. So if you got questions, please email me, or when you come in Thursday, you can ask questions too. We'll meet again Thursday, 4 o'clock, and take some questions, and then dive off into the next couple of sections that we're going to do. Should be a pretty light day on Thursday, so it shouldn't be too bad. All right.